So without further ado, let's get into what today's seminar is about, which is simulating physics with superconducting qubits, presented by Gal Gumpel. Gal is a PhD student at Technion, aka Israel Institute of Technology, and works in the Superconducting Quantum Circuits Lab, where he researches implementations of quantum simulations in continuous variable quantum computing. He also studied his master's at Technion, during which he developed quantum imaging techniques for astronomy. And contrary to the stereotype about physicists, Gal prefers dogs to cats. And I'd have to agree with you on that one. Dogs are definitely superior. So, Gal, the virtual stage is yours. And to our audience members, please don't hesitate to put any questions in the chat. We'll have a 30-minute Q&A after.
Thank you, Sabina. So excited to be here, and I hope you will enjoy this presentation as much as I enjoyed making it. And just a moment. Okay, so let's make sure everybody sees it. Do you see the presentation?
Yep.
Great. So that okay. So I'm gonna pay a little tribute to a talk by Feynman that was made about 40 years ago. Feynman, a very famous physicist, gave a keynote talk in the first conference on computers and physics, and he discussed the idea of simulating physics with computers. And it is believed that this keynote talk by Feynman was the initiator of this whole field that we now call quantum computers. And so I took the idea for the title from Feynman's own talk. The title of Feynman's talk was Simulated Physics with Computers, and I will talk about a certain kind of quantum computers. And so usually when I tell people what I do in my PhD, they ask me a series of questions. And the first is, what is quantum computer? So I need to explain what is a quantum computer before I start explaining what I do with quantum computers. So I'll try to give a good explanation. By good explanation, I mean there are a lot of videos on YouTube and a lot of popular articles on the web that you can find about quantum computing, and many of them are good articles, but many of them are not so good articles. And I'll try to give you the right notion about what is a quantum computer and what's so special about them. And I'll try to avoid the common misconceptions about quantum computers that even physicists get it wrong sometimes. So first of all, I want to recommend you about some sources that you can learn from if you want to study about quantum computers. Then I suggest you first go to the popular sources like the blog of Scott Aronson, computer scientist who works in the field of quantum computing. He also he created a nice comic strip about quantum computing, the SMBC comics, and he has a nice TED talk that you can also watch. Besides that, if you want to deepen your knowledge in quantum computing, then you are highly recommended to you read at least one of those books. Those are the most popular and most thorough books in quantum computing. And of course, I highly suggest to read at least once the article of Richard Feynman from his talk about simulating physics with computers. It's a very accessible as Feynman always was a great explainer. So I highly suggest to read it at least once. And now, before we start to talk about quantum computers, let's gauge the level about what is a computer. So whenever you ask someone to explain how a computer works, I guess that you always, or most of the time, you will get this pictorial explanation of something along the lines of you have a black box, and inside this black box you have switches that can go on and off, and you set these switches in an on and off combination in some order, and that order of on and off switches determines what the computer will do. So this is how a computer works. And that's quite a good explanation of how a computer works, without getting into mathematical, deep mathematical description. Quantum computers, however, are more complicated. And when I said I want to give a good explanation, I meant that most popular explanations will tell you something about qubits can be both on and off, or 0 and 1, but actually that's not an accurate description of what the qubit is and how a quantum computer works. And I will have to go a little bit into mathematics, but not too much. So I'll try to keep it simple. So what a quantum computer is and how does it work? So unlike classical bits that can be either 0 or 1, a quantum bit, what we call a qubit, can be any linear combination of zeros and ones, of ons and offs. What I mean by a linear combination is something like that. I have a linear sum of two states. State 1 is on, and state 1, the other state is off. And they have some amplitudes multiplied there. These amplitudes tell us something about the state. We don't know yet what it tells us, but we do know that some of the properties of these amplitudes. So these amplitudes are complex numbers, so they can be either positive numbers, negative numbers, or even a square root of a negative number, which is a complex number. Another thing we know about them is that they are related to the probability of measuring the state of the qubit by something we call Born rule. Born rule is a postulate that states that the probability to measure, for example, I think I have a mistake in the on state, not the off state, is the amplitude of the on state squared, and the probability to measure the off state is the amplitude of the off state squared. Okay, so.
Hey, Gal, sorry to
Yeah.
interrupt. Are you sharing? What we're seeing is your cover slide still.
Oh, wait a second. I see my own slide, but maybe. Second.
Yep, there we go. Slide 5.
Yeah.
Okay.
And maybe I'm in presenter mode.
It may be that presentation mode shows it off a different screen.
Yeah, now you see the fifth slide?
Yes.
Okay. So I'll repeat the explanation. Let's stay in the first slide. So as I said, the qubit is a linear combination of two possible states, of being in a on state and being in an off state of the switch. Now, we must be careful when we say linear, a superposition or linear combination, because that's when things can go wrong in the explanation. It doesn't mean that the qubit is both on and off at the same time, or the qubit is with some probability on or with some probability off. Both descriptions are wrong. The linear combination means that we are in some kind of a superposition of being in one state and another state. And I keep using this word superposition because it doesn't have a classical interpretation. The amplitudes are related to probabilities through some rule that Born postulated almost 90 years ago. This is called the Born rule, which states that the amplitude squared gives us the probability to measure one state or another. But we also know that these amplitudes can be complex numbers, and I'll elaborate more about why is it important that they can be complex numbers. So another thing important to mention here is that from Born rule, we can also imply that the sum of the squares of the amplitudes must be 1, because this is the probability to measure any state of the system. So with that, let's move on. I'm now in slide 6, so if you don't see slide 6, please tell me. So now most of the people will ask, so what's the big deal? It sounds like a deterministic, probabilistic computer. You have a bit that has some probability to be in 0 state and some probability to be in 1 state. We can make this in a classical way. We can make classical probabilistic bits. So the answer is no, it's not just a probabilistic computer. We don't only have a probability to measure 0 and a probability to measure 1. We also have something that's called phase. So let's look on 2 states, psi1 and psi2. That's a way. By the way, I didn't mention it, but these weird signs, they are called cats. And this is a way to represent a state, a quantum state. So psi1 is a linear combination of alpha 0 plus beta 1. And psi2 is a linear combination of alpha 0 minus beta 1. Now, if we look only on the probabilities, then we can see that the probability to measure 0 at both states is the same. And the probability to measure 1 in both states is the same. So what's the difference between the states? The difference is the sign. And the sign is a relative phase between the 0 state and the 1 state. Now, phases, is like my mentors in my master's always told me, phases are everything that's important in physics, and everything interesting in physics always end up to be a phase. So these phases are interesting because it means that we can interfere between different phases, between different states. For example, if I have a state 1 with amplitude beta and probability and a phase plus, and state 1 with amplitude beta with phase minus, if I sum them, then I can eliminate the possibility of being in state 1. So this is roughly an explanation of what interference is between states. So I can use these interferences to cancel out paths that are leading to wrong answers and reinforce paths that are leading to right answers. So to put it in simple words, the whole idea of quantum computing is to engineer an interference pattern such that I will have a much larger probability to get to the right answer than to any other of the wrong answers. So that is what quantum computer is, and that is the power of quantum computers. And there's nothing related to being in many states in parallel and doing parallel computations. That's a wrong interpretation of the whole idea. So if we sum it up, a quantum computer is not a faster computer, is not a smaller computer, and it can't solve all problems in a single run. What it is a, first of all, a fundamentally different way to process information. So classical computers works with classical probabilities, numbers between 0 and 1, and quantum computers works with what we call probability amplitudes, which can be complex and can interfere. And that's a whole different way of processing information. It's a certain kind of generalization of the probability theory. Also, it exploits the fact that our world is governed by the rules of quantum mechanics. So in the most pure way, quantum computers follow the rules of quantum mechanics, much like how the real world works at very small scales. Molecules, materials, and even complex biological processes are governed by the rules of quantum mechanics. And if we have a computer that is governed by the same rule, then it will be much easier to simulate such systems. And of course, it can solve some problems asymptotically faster if we can build it. But I'm saying that, in my opinion, this is not the most important thing about quantum computers. I think the most important thing about quantum computers and the great promise of quantum computers is point number 2, that we can simulate quantum mechanical systems in a much more natural way. So we roughly explained what quantum computer is and what is the qubit and what the difference between a qubit and a bit. But what are these qubits made of? So that's the
Sorry,
second
Gal,
question.
before you go
Yeah.
on, we're still on slide 5.
I'm still
Can
on
you
slide
bring-
5. Oh,
Yeah. Okay, now we're on slide 9.
yeah, I think I'll stay on this. I think I'll stay with this display, just to be sure that you see what I see. Okay. So now that we understand what a quantum computer is in theory and what the difference between quantum computer and the classical computer, we want to know how we build a quantum computer. What is this quantum switch? Because in computers, we know we have transistors. And transistors act like a switch in a certain regime. So they can be turned on and off individually to control the operation of the computer. But how do we make a qubit, quantum switch? So there are many platforms to build a quantum computer. The most common platforms are cold neutral atoms, quantum dots, photons on chip, superconducting circuits, and trapped ions. Each and every platform has its own pros and cons, and I'll try to discuss it later in a bit more details, but roughly describing the state of each platform right now. So cold neutral atoms are a great platform for many body quantum simulations. Many body, I mean quantum simulations of systems that are made of many components, like many atoms, or complex systems made of many molecules, for example, lattice models. Quantum dots dots are a good platform for quantum communication. They are not in the lead right now for quantum computation, but for quantum communication, they are in the forefront. Photons on chip is also a leading platform, one of the three leading platform quantum computation. The other one of the three leading platform is trapped ions, with companies like IonQ in the US. For photons on chip, you have companies like Xanadu from Canada, if I'm not wrong, and superconducting circuits, which arguably is the leading technology right now in quantum computing. And I mean leading because all of the big tech companies chose to use this platform, IBM, Google, Amazon. So for right now, it's the leading platform. It doesn't mean that it will win the race for quantum for leading quantum computer. And I think all companies and all physicists right now agree that the future of quantum computer will be some hybrid model of several platforms like superconducting qubits, ions, and photons. But in general, today, the leading platform is superconducting circuits. So what are these circuits? So you always see this image of this golden chandelier when you look for the word quantum computer, and actually we'll show you at the end a slide like that from Google search. And this golden chandelier, besides being very beautiful and really nice image to share, it's the cooling system of these chips. So the superconducting chips, superconducting circuits could only act in a very low temperature as quantum circuits. When they are operated at high temperatures, when they operate at high temperatures, they don't act in a quantum way, but in a classical way. So this is the first thing you should know about quantum circuits. This is why we need this golden chandelier. On this image at the top right, you can see an example of a chip that being used in quantum computing. So in this chip, you can see some resonators that I will explain later what it means, and some qubits that are sitting right here in this line. They are they are sitting right here in this line. You can almost you can't see them because they're very tiny compared to the whole system, and I'll explain that in a moment. So how do we make electrical circuits to be quantum and to act like a qubit. So we took an idea from a field called cavity QED. Cavity QED is a field that researchers how atoms interacts with light inside cavities. So you take an atom, you put that in an optical cavity between two mirrors, for example, and you shine a light on it. It can be a light from a laser or any other source of light, and you measure the interaction between the atom and the light, and in cavity QED, you can show that it is possible to control the state of the atom using the light you shine on it, or you can also control the state of the light in the optical cavity using the atom you insert into the cavity. So with this idea, we do something very similar. We take electrical circuits that in some way act like an atom, and then I will explain in the next slide how is it acting like an atom. And we shine a light on it, not a light in the optical regime, but a light in the RF and microwave regime, radio frequency and microwave frequency regime. So those frequencies are like the frequencies that used for the cellular communication. So that's why we put an iPhone here. So we can send signals of microwave frequency to the circuits, and the circuit sits inside a cavity in the of microwave frequencies, and that's how we can control the circuit like atoms can be controlled with the laser in the optical cavity. So similar to the idea of cavity QED, we use the name circuit QED to describe the platform we use and the physics behind this platform. So how does it work? So we have a circuit usually made of aluminum. Aluminum in very low temperatures below 1 Kelvin, which is 1 degree above the absolute zero, becomes a superconducting material. It means that all the electrons flow together with no resistance, with no dissipation. And besides having the two usual components that any electrical circuit can have, the inductor and the capacitor, we also have another component, which we call the Josephson junction. Josephson junction is a sandwich of superconductor, insulator, superconductor. And when the insulator is only few nanometers thick, then we can we can observe an effect of tunneling. And by tunneling, I mean the electrons can flow from one superconducting island to the other superconducting island, while by tunneling through this barrier of the insulator. So although there is an insulator between these two islands, the electrons can still flow from one island to the other. This is a quantum effect. And what's special about this component is that it is a non-linear component. So by non-linear, I mean that it adds a non-linear dependency of the circuit on the state of the cavity, on the state of the light inside the cavity we put it in. So with these components, we can build, we can engineer many types of electrical circuits. And like the periodic table of atoms, we can have a periodic table of artificial atoms. And we have many of them. We have a simple harmonic oscillator, which is just an LC resonator. LC resonator is an inductor and capacitor in parallel or in series. We can have the transmon, which is the most popular artificial atom used in most companies today. IBM uses transmon, so Google uses transmon. We can also have other types of artificial atoms like the flux qubit and the fluxonium, which is quite new, and the Cooper pairs, which is the first artificial atom that was suggested. And each of these artificial atoms, as you can see, have its own landscape of energy. And by knowing the energies and engineering the properties of the capacitor and the inductor and the Josephson junctions, we can set the frequency of this artificial atom, and using photons with that frequency, we can control this artificial atom. Let's take a closer look on a transmon. So this is a chip that has a transmon on it. The size of the chip, as you can see, is much smaller than 5-cent coin, 5 euro cent actually. On this chip, we have these two plates, and between these two plates, we have these two overlapping lines of aluminum. The two plates are the capacitor. So if we look at this circuit, then the two plates are this capacitor. And the two overlapping lines of aluminum are the sandwich of the superconductor insulator superconductor. So we make one line of aluminum, we oxidize it, the oxide, the oxidized thickness, the oxidation thickness is about few nanometers, and then we put another line of aluminum, we make another line of aluminum overlapping with it. So we have a sandwich of aluminum, oxidized aluminum, and again a pure aluminum. The pure aluminum is the superconductor, and the oxidized material between them is an insulator. So this circuit is a simple transmon. This is why, by the way, most of the companies use transmon. It's the most simple to fabricate, just two parallel plate capacitors and overlapping sandwich of aluminum oxide aluminum. And all of these goes into a cavity. This is a microwave cavity. The size of it is a few millimeters to a few centimeters. And inside this cavity, we put an antenna, and this antenna is the way we send microwave signals inside the cavity and read microwave signals out of the cavity. So this is a basic circuit QED, basic circuit QED object, just a qubit inside the 3D cavity. Another way to fabricate these qubits and cavities is in 2D 2D architecture. So in 2D architecture, we have again the qubits that sit here, and here you can see the parallel plate capacitor. The Josephson junction in the middle is too small to be seen, and it is coupled to what we call a resonator. A resonator is much like a 3D cavity, but in 2D. So this is a 2D architecture of a transmon coupled to a cavity. And on the chip, we have a transmission line, and through the transmission line, we can put signals into the resonator, and we can read signals out of the resonator. So the 2D architecture is the most common in the industry. Google, IBM, and everybody else uses the 2D architecture because it is much easier to fabricate and has the greater potential to be scaled up. But 3D architecture has its own pros, and I will discuss it in a few slides. We use in the lab both architectures, and we use the 3D architecture for something called bosonic encoding, which I will explain also in a few slides. So how does a full quantum computing system looks like? So it looks something like that. We have this dilution fridge. Inside this dilution fridge, there is the famous golden chandelier. And inside this chandelier, and inside this dilution fridge, we put our systems. So for example, the cavity you saw here with the chip inside it is put right here on the bottom part of this chandelier. And the bottom part of the chandelier, the lowest stage is in temperature of about 10 millikelvin. So it is a really low temperature, way below what is needed for the aluminum to become a superconductor. And from this dilution fridge, there are several wires goes out and connected to the electronics in the lab. And the electronics are controlled from classical computers. So classical computers are still useful. And we send signals and read signals using all these electronics here. And so just to give you an intuition of how it works. Okay. I hope you see now the slide that I show you. So I just want you to see this better, so I'll enlarge the slide. So what we do is we put a signal in the cavity. This is how we measure a qubit. We put a signal in the cavity. The signal interacts with the qubit, and then it goes out. Now we the blue and the red describe the signal that the blue describe the signal that is related to the 0 state, and the red describe the signal that is related to the 1 state. I will explain to you in a minute what does it mean. The overall signal goes out of the cavity, and it goes through several splitters and several modulators. Then it goes through a quantum amplifier, and this amplifier amplifies the signal with minimal noise, and then we can read this signal. So what you see here is a readout at the right bottom part of this slide. You can see just a continuous readout of the voltage versus time, and the blue line is the threshold for the 0 state, and the red line is the threshold for the 1 state. So every time the voltage jumps above the blue line, we know we are in the 0 state. Every time it goes below the red line, we know we are in the 1 state. So how do we measure it? We need to understand first that we have two frequencies in the system. One frequency is the frequency of the cavity, for example, in this case, 7 gigahertz. And one frequency is the frequency of the qubit, in this case, 5 gigahertz. To perform an operation on the qubit, we must send a signal at the frequency of the qubit. But to read the state of the qubit, we send a signal in the frequency of the cavity. And through the cavity, through the state of the cavity, we know what the state of the qubit is. So what you see here is a plot of the what we call the phase, the phase of the resonance mode in the cavity. This is the reflected phase, which means this is the relative phase of the signal that goes out of the system relative to the signal that goes in. So we assume the signal that goes in comes in a phase that equals 0, for example, and we measure the phase of the signal that goes out of the system relative to the signal that we send it to the system, and this is what makes this shift. So whenever the qubit is in the 0 state, we measure this curve, blue curve, and whenever the qubit is in the 1 state, we measure the red curve. So this is what sets the threshold lines, the blue and the red lines here, and in that way we can measure if we are in the 0 state or the 1 state. So this is a simple measurement of a qubit. Now, encoding qubit in a transmon is one way, but we can also do a different thing. We can also encode the information in the cavity itself, in the photons in the cavity itself. So as I mentioned before, in cavity QED, it is possible to control and measure the state of the atom using photons sent into the cavity, but it is also possible to measure the state of the cavity and control the state of the cavity by sending in atoms and measuring their states. So in a very similar way, we control the state of the cavity, for example, the phase of the reflected signal from the cavity, by controlling the state of the qubit. We can also control the photons inside the cavity by sending signals to the qubit and changing state. And also, we can also read the state of the cavity by sending signals in the frequency of the qubit and reading the qubit. So the qubit is also affected by the state of the photons in the cavity. So what you see here are different representations of photonic states inside cavities. These particular representations are called Wigner functions, and this is very similar to a probability function, but not exactly, because it can be negative, as we explained before. Probabilities in the quantum world can be negative. So we call that a quasi-probability distribution, and the shape of this distribution can tell us a lot of information about the state of the qubit inside about the states of the photons inside the cavity. And so one of example of how we can encode a qubit in the cavity in the transmon is by what we call a cat code. Cat code is the most simple example of bosonic encoding. Bosonic encoding is called bosonic encoding because photons are some kind of bosonic particles. We will not dive into it in this presentation, but I just mentioned it. So one way to encode information is by the cat code. So it is possible to set a certain state of the cavity we call a coherent state as the zero state, as the logical zero, the qubit, and you can also set the opposite coherent state. This is the coherent state with a minus phase, like we saw before, that can have a phase of plus or minus before the amplitude of the state. So first of all, we can show that the states are orthogonal, which means that are not linearly dependent on one another. So we can encode the zero state in one of them and the one state in the other. And we can also have two superpositions of the states, which represent superpositions of 0 and 1 states in a quantum bit. So like we saw, we can have alpha 1 plus alpha 0 plus beta 1. So in this case, alpha and beta are equal, and there is a plus sign between them. And of course, the orthogonal state of this state is the same one with a minus sign. And so this is a way to encode the information in the state of the photons in the cavity instead of the state of the transmon. I'll skip that slide for a moment. I'll come back to this later. So we have two ways to encode information. One is in the state of the transmon. So the transmon can be in the ground state or in the excited state like an atom, or we can encode information in the photons in the cavity. So they can be in either a coherent state with a plus sign or a coherent state with a minus sign. And this is the 0 and 1 states of the logical 0 and 1 states of the qubits we encoded. So why should we encode information in cavities, and why should we use 3D cavities to do that? So first of all, to have a good qubit, we need the qubit to have a long coherence time. Coherence time is the time that the qubit loses its information. So we can't know what the qubit is, what the qubit was, in what state, and also a long relaxation time, which is the time that takes the qubit to fall from the excited state to the ground state. And if we are taking the picture of atoms, for example. So apparently, 3D cavities have a very long relaxation times and a very long coherence time, or dephasing time, called here T2, and that's why it's a very active field right now, because it may be more efficient to use to encode information in the states of the cavity instead in the states of a physical qubit, of a physical transmon. Moreover, there are many architectures when you go to 3D that allow to have several modes in one cavity. So you can have several resonators in a single cavity. That's the idea. And that's also another way to scale up. I must say that 3D cavities are not leading candidates in the quantum computing industry, but they are very interesting, although they are not leading candidates, and many interesting phenomena and many interesting physics can be studied with 3D cavities. And also, it is much easier to create a correctable qubits, qubits that can be corrected in real time using photonic states instead of transmons or any other kind of artificial atom made of circuit. So that's also why 3D cavities and bosonic encoding is studied much more intensively in recent years. So what you see, by the way, is a real measurement of a spatial state in a cavity called GKP. And what's special about it is that the state can be corrected in real time, and that's of course the main goal of quantum computers in the future, to have qubits that can be corrected in real time, so that we can prolong their lifetime and their coherence time as much as possible. So if someone will ever ask you or we have which technological platform to choose, then the answer is the one that give you the best ratio of coherence time to gate speed. Gate speed is how fast you can perform gates and operations on using these qubits, and coherence time is how much time the qubit can hold before you lose the information. And so the platform that will give the best ratio of coherence time to gate speed is the technological platform I will suggest you to invest in. And there is also the third point, which is scalability, but as for now, all platforms are not so scalable, and scalability is really a difficult problem in all platforms. So just to give you an idea of where are we standing right now in terms of coherence time and gate speeds. So if we look, and all of these are different kinds of artificial atoms and architectures. You can see some of them are transmon in 3D cavities. We also have transmon in 2D cavities. And this graph shows us the lifetime of these artificial atoms as a function of the current year of the year they were invented and measured. And you can see that today we're standing in a quite good place. We're always we are constantly reaching to higher and higher lifetimes. So right now we are standing about 10 to the 3 microseconds, about 1 millisecond lifetime, which is, it sounds like very low, but it's really long enough time for a qubit. And we also have some qubits that are partially error corrected, as you can see, but they are denoted with the X sign on them. So if you look at this graph, then you can see that we are advancing towards better and better artificial atoms and better and better qubits. But you can also notice that there is some kind of an asymptotic relaxation here, and I hope we will break this barrier and keep going to higher coherence time and our higher lifetimes. And the other table I want to show you is the gate time. So all of these are real gate times. Those are gates that were performed on real qubits. Some of them are, all of them are actually 2-qubit gates, which are considered to be the most important gates for quantum computing. Those are the gates that can entangle different qubits. And you can see that most of the gates these days, state of the art, are at tens of nanoseconds. Some of them are at hundreds of nanoseconds. So we're really at a good point where we can perform hundreds of operations, hundreds of gates before a qubit loses its information, but it's still not enough. Not enough because of what we call fidelity, and this is how good the gate is, or what is the probability of the gate to perform exactly what I wanted it to perform and not to give me an error. And although you see that the fidelities are 99 point something percent, it's not enough. It should be 99.9999999% to be accurate enough for quantum applications. So that's the reason we are looking for error-corrected qubits that we can correct them on the go in real time while we perform these gates. So we perform a gate, the qubit may have an error caused by the gate, and we can correct it in real time. So this is the holy grail of quantum computing, still found from forage. So I promised you I'll show you the quantum computer Google search. So if you look in Google for a quantum computer, you see this set of images of the golden chandelier that it's only the cooling system of the computer. But you can also notice that you almost can't see any other platform besides this platform. So this dilution fridges are used only for a circuit QED platform. You can't find any image of, at least not in the first results, you will not find images of ion-based quantum computers or photonic-based quantum computers. And I think this shows how popular this platform is. That, again, doesn't mean that it will be the winning platform in this race, but it's surely the most popular one, and the platform that was invested by most of the tech companies today. So we do know, or we do slightly understand what a quantum computer is. We do slightly understand how qubits look like and what they are made of. But now raises the question, so, okay, let's assume we have a quantum computer. What we can do with it? Why do we need it? Is there anything we can do with the best computers we have today? And of course, the answer is yes, there is something. And I want to put just the whole the maybe the most famous quote from the same lecture Feynman gave 40 years ago. When he concluded his talk, he said, "Nature isn't classical, and if you want to make a simulation of nature, you would better make it quantum mechanical." And that's the whole point, I think, of quantum computing. Nature governed by the rules of quantum mechanics, molecules, atoms, photons, lattices of any kind of atoms, quasi-particles, high energy physics, even cosmological research. All of these are governed by the same rules of quantum mechanics. And if we want to simulate them in an efficient way, we must use a computer that is governed by the same rules. So if you ask me, the great promise of quantum computers is actually quantum simulations, not, I know everybody talks about cryptography and breaking the RSA and breaking into every bank account in the world and taking all of your money, but that's not a great promise of quantum computers, and it's also not very close to be applicable in the near future. What does interesting and what does and what it will make a change, I think, in the world when we will have an operative quantum computer is the ability to simulate quantum systems and to develop new drugs, develop new materials, and even solve complex problems like optimization problems for the industry, and for find new materials for efficient energy transfer. So this is the great promise, I think, of quantum computers. And now
Uh-oh, I think you're
explain what is
cutting
quantum
out a
simulation.
little bit.
So a quantum simulator is, do you hear me now?
Yes, you cut out a little bit in the last two sentences.
Okay, so I'll repeat the last sentences. A quantum simulator is a device that allows us to study quantum systems in a programmable fashion. And it means that we can program this device to act like a quantum system that we want to study. And we can control all of the parameters of the system. And that's that in that way we can simulate the natural quantum system we want to study in a more controllable way. And to understand how it works, and what are the properties of the system, and what we can do with it. So there are two approaches to quantum. One is the analog simulator, which is indeed which usually prepare to be intrinsically as similar as possible to the model we want. a digital simulator is a more general purpose simulator. We can simulate every model we want on the simulator. And in this approach, what we do, we take the Hamiltonian here, but if you don't know what Hamiltonian is, then it doesn't matter. Just we take the quantum mechanical description of the system, the equations that describe the system. We decompose these equations into elementary gates that we can perform on this device, like a computer. And then we perform these gates in a certain order, and this order in a digital way repeats the same dynamics we wanted to study. So this is a more general purpose simulator, and it is more difficult to engineer theoretically and practically. And down here, I give you just a classical example of what an analog simulator is. So, for example, an LC circuit with an inductor and a capacitor can be an analog simulator of a mass connected to a spring. So, if you take a mass, the mass, and you move it, you shift it by a certain amount length, and you let the system evolve, then you have oscillations of the mass along the line of the spring. So you can say that the system exchange energy from the energy stored in the motion of the mass, we call it kinetic energy, and the energy of stored in the spring, we call it potential energy. So we have some kind of interaction between the mass and the spring, and the exchange energy between them in a oscillatory way. And a similar thing happens in an LC circuit. The inductor and capacitor exchange energy between them in an oscillatory way, exactly the same way as the masses and spring does. So an LC circuit can be said to be an analog simulator of the mass and spring model. Of course, there is no use for such a simulator. We can use the original system of mass and springs in lab. It's not a complicated system, but just for just to get the idea of what a quantum simulator, an analog quantum simulator is. So an analog simulator is something like this. This is an electrical circuit that is engineered to act like a mechanical system. So in a very broad range of in a very broad sense of yeah, you can see here that in the same way we can engineer electrical circuits to act like, for example, light harvesting molecules. So this is a real paper from Nature Communications, a real electrical circuits, quantum circuit with transmons and resonators that models the way that light harvesting molecules work. So this is a way to study light harvesting models for example, for light harvesting materials and for solar cells. And another example is this paper, another paper from Nature, that simulates using, again, transmons and resonators, a model of a model called Bose-Hubbard chain. This is a model that can that is related to some something that called a multi-insulator, some kind of topological phase, a material that can conduct on the surface, but is an insulator inside its body. So that's another example of quantum simulation of a real physical model of a topological material. Another example of quantum simulation is this quantum simulation of another topological model. In this simulation, they used something that called quantum walks. It's very, if you are computer scientists, that you are probably familiar with the idea of a random walk. So random walk is a very popular algorithm that is used in many applications like searching and stochastic simulations. So this is a generalization of this idea, a quantum walker that works on a closed loop, and it simulates very interesting phenomena in physics. And another example of simulation of the molecular vibrations of triatomic molecules. So we can see the H2O here, and you can see the free oxygen molecule model here. All of these spikes are the frequencies of the different frequencies of the molecular vibrations available in the system. And it was simulated by a simple system of 2 transmons and 3 resonators. So so it's quite amazing to see what a simple device with just few qubits and few resonators can do. This calculation is very difficult to do on classical computers. It takes a lot of time. Still, it still doesn't give us any quantum advantage because all of these calculations can be calculated analytically, but it's a nice proof of concept and a very nice example of what quantum computers can do. And I hope it gives you an idea of where quantum computers are going and what quantum computers will be used in the future. And I'll leave the rest of the talk for your questions. If you want to ask me about things I said here or about my own research, which I didn't mention here, then you are more than welcome.
Wow, that was a lot, but it was very fascinating. Thank you so much for taking a really deep dive into superconducting quantum computers, how they work, and what we can do with them. We do have a couple questions. Thank you to those who direct messaged me some questions. I think our first one is more general and is, what piqued your interest or drove you to pursue this field, and why superconducting qubits?
Okay, so I'll be honest and I say that at first I wasn't really wanted to go into this field. It looked like it is very complicated and more mathematical than I wanted to. And then as a physicist, I don't really like mathematics, but But my supervisor, Shai, which is now my supervisor, reached out to me when I took a course that he taught about atoms and photons, and he just raised my interest in this field. And I came and decided to work with him in my PhD, and I'm very glad that I chose to go into this field, especially the quantum simulation, the field of quantum simulations, which is a fascinating field. of- It's still a very difficult field as I thought, but it's very fascinating, and I'm glad I chose it.
Well, we're glad that you're in this field and here presenting. A question from Elisa, what do you think the main challenges are for superconducting qubits in the future?
The main challenges of superconducting qubits. Well, I think there are several challenges which I already mentioned. One of them is the scalability, which is a challenge in all the platforms, but I think that for superconducting qubits is a great challenge, because there is a limit of how small can we make these circuits, and how much crowded we can have them on the chip. And I think the other challenges actually to find new materials and new architectures that will give us better performance of these circuits. And by better performance, I mean longer coherence time, longer lifetime. And the qubits that we have today are great qubits, but they are still very noisy and very sensitive to the environment. And so we need to find ways to keep them and as protected as we can from the environment, and make them less sensitive to noises that we have inside the dilution fridge.
Mhm. What are your personal thoughts about how we could go about reducing that noise?
Well, there are several ideas, and one of them we also work on it in our lab, not my personal work, but one of the projects we have in the lab is what is an idea to combine different superconductors on the same chip in such a way that some of the superconductors will act like traps for something that we call quasi-particles that cause noise in the superconducting devices. So quasi-particle traps is one approach for that. There are many other approaches, and of course, there is always the approach of encoding the information in photons instead of in the electrical circuits, and in that way to make them more robust to noise.
Wow, I mean, we definitely have a long way to go. And I think you briefly mentioned that one of those ways is something that you are working on personally. So we'd love to hear more about your work.
Right. Yeah, so my personal interest right now is to build and to engineer an analog quantum simulator for the Dirac equation. So Dirac equation is an equation that describes that combines special relativity with quantum mechanics. So it describes how, for example, particles in accelerators behave, or another interesting thing that this equation describes, and quite surprising, is how particles in two-dimensional materials behave. And these two systems, high energy particles and 2D materials, are very interesting systems, and there's a lot of interest in the physical community and in other communities to study these systems, 2D materials for material science, and for new and better devices, better electronic devices, and high energy physics to understand better the basics and fundamentals of the quantum theory. So in my research, I try to engineer a system that will act like the Dirac equation, and in that way I could study all these set of systems that follow this equation.
Wow, that's really fascinating. And you were talking about how we're building these simulators and also advancing quantum technology. What quantum innovation do you think will be the most impactful on society as a whole?
That's a difficult one. Well, I think the first and maybe the most interesting application of quantum simulations is the quantum chemistry quantum simulation, because these quantum simulations could help us develop new drugs and new materials. And I think that's the most interesting and in the industry right now. Actually, most of the quantum simulation papers, most of the quantum simulation groups work on quantum chemistry simulations, for that reason, I guess. So I think the quantum chemistry simulations are the most impactful right now.
Okay. And so with that, do you estimate that more companies will invest in quantum simulators specifically for quantum chemistry and all of its impacts on developing better drugs, vaccines, et cetera?
I'm sorry, can you repeat it?
Oh, yeah, of course. What, with that, as you expect quantum simulators to really impact quantum chemistry, do you expect more companies to start investing in quantum simulators specifically? As you were saying earlier in your presentation, a lot of people are talking about quantum cryptography, et cetera. So what do you think about companies specifically investing in quantum simulators?
So first of all, there is a great increase in the last decade in investments in quantum simulations specifically, but and I think this will keep growing in the near future, and maybe also in the far future. I think that quantum simulations, especially the quantum chemistry simulations, can have near-term results. As I showed in the second, as I showed in this slide, there are already operating simulators for very simple quantum chemistry models, but they already work with all the noise and all the problems that quantum computers have these days. So I think that the great investment that has right now in quantum simulations and the great investments that will come in the near future will bring us better and better results. And I think that actually, I do believe that actually the first real life application, practical application of a quantum computer that we will have in the future will be related to simulating some kind of drug or new material. I think that's the first thing we see before even cryptography.
Mhm. Yeah, definitely a much more near future achievement compared to quantum cryptography. Speaking of the future, how do you see your own role in the quantum space evolving over the next few years?
So I'm interested, of course, in keep doing research and staying in the academia. And so I will pursue, I guess, research positions in academia in the future. And I have a lot of interest right now in how quantum physics affects biological processes. So I think that whatever I'll do in the future will be related to this field, this new emerging field. And I also think that it is related in some way to quantum computing because the way quantum physics, quantum mechanics affects biology is very complicated, because biological environment is very noisy, and it is highly difficult to simulate the many particles of the biological system and how they interact with each other, and how a DNA is written, and how mutations are caused, and it's all quantum mechanical in this sense. So I think that the next evolution of quantum computers will probably have to simulate some quantum biological effects, and that's, I think, my future interest.
Okay. Speaking of next steps, what is your biggest piece of advice to all of our participants, our audience listening in right now?
So first of all, I suggest that whatever you do, follow your interest, follow your curiosity, and don't try to do what everybody else do, and don't try to do something because that's what most of the community doing right now. And I know that many people does it because they think in that way they will advance faster in science or in the industry, but actually the greatest achievements and the greatest scientists were always driven by curiosity. So if you do interested in going into this field and being a researcher, just be driven by curiosity.
That's very powerful advice. Curiosity is definitely the most powerful thing. Well, thank you so much. I know we ran a couple minutes over, but thank you so much, Gal, for presenting. And thank you to all of our audience members. And thank you to anyone listening in the future, because this is recorded and will be posted on Girls in Quantum website, Discord, YouTube, LinkedIn, Instagram, etc. So thank you to everyone for tuning in, and thank you again so much for talking about this.
Thank you. It was a pleasure.
Of course. And I will reach out later and compile a list of all of the resources you talked about through your presentation and see if we can get that out to the greater quantum community, the Girls in Quantum community. Okay.
Great.
Thank you,
Thank you.
everyone. Have a nice morning, afternoon, or evening, wherever you are. Bye.